Welcome back to Mechanics and Control of Robotic Manipulator. Last few classes we have seen robot kinematics, dynamics and all other detail. Based on the request, what I thought I can actually give some examples related to frame arrangement and as well as something like how to obtain the kinematic model. And later on I will show how to derive dynamic model and other aspect in consecutive series. So as I already did some kind of supplement, so this is also one kind of supplement, but here would be focusing some example. So even this examples will come several. So I would be start with the first example on SCARA manipulator. Okay, so the as similar we were actually giving a disclaimer. So now we will come to this. This is actually like example related to robot kinematics. I will be talking about the first example which is related to SCARA, which is very close to your exam portion. That's why I thought I can actually give it this. So in that I will be showing in this particular video, I will be showing several things. So I will be showing how to fix a frame arrangement based on the given, you can say as a diagram or you can say arrangement, how we can fix the frame, then how to obtain the D-H parameter. Once you obtain the D-H parameter, then you can actually obtain transformation matrix, then you can obtain both forward and inverse kinematic model. That's what we are going to see in this particular short video. Okay, so now you can see that this is the question which given to you, or you can say this is the general manipulator, which is one of the popular manipulator called SCARA, right? So this particular manipulator is having 4 degrees of freedom. You can see it is actually having one rotation here, another rotation here, and there is one translation here and another rotation here, and the positive direction of rotation and as well as translations all given here. And what they were asking, or you can say what I was asking in the, I was actually asking you to do in the exam. So forward and inverse kinematic model of this particular robot. You can see that this, if you look at in the top view, how it look like. I'm just showing this is my view. So this way it's like this. The top view says like this. Okay, so there is one motor here which is this. So there is another motor which is here, and there is another motor and translation motor also there. In the sense there is a linear and as well as rotary motors are here, and there is a rotary motor here and another rotary. The same thing if you are looking in the front view. So I can show this is actually you can see this is one actuation and this is another actuation, and you have a translation and then you have a rotation. Okay, so like that. But you can see that the positive rotation is actually given. So this is actually going up based on the configuration. This is also going up, and here you can see that this is actually translation positive is this, so in the sense up, and the rotation is actually the other way around, so it is actually down. Okay, so based on the given, you can say the positive direction, I am fixing the joint axis. So before going to see this, I'll just give a small, you can say, recap. So while we are actually fixing frame arrangement, what we have to see, so we have to fix the z axis to the joint axis, that you all know. And second thing is what we can see, the frame location you need to find. So if it is actually both are parallel, then you have several possibility. If it is actually intersecting, then you can actually take the intersecting point as the, you call frame, or you can say the location of the frame or the coordinate frame. If it is actually non-intersecting, but it is actually orthogonal axis, then you have to see how to fix it. Okay, so these are the things we are actually seen in the you can say previous lectures. So I'm just giving a recap. And what the next step, once you fix the z axis, then you have to fix the z0 axis, and based on the z0 and z1, you have to start with x0 to all, you can say up to xn axis. So what you know, if x axis you want to fix it, this x axis is actually going to be the rotating axis of zi in order to make it parallel to zi plus 1. So in the sense you have to see these two, how it is arranged. If these two are actually perpendicular, then the xi would be, you can say, normal to the plane which is consisting of the zi and zi plus 1. If it is actually parallel, then you can actually take it the common normal, right? These all we have seen, right? After that, what we have seen, that the link length cannot be negative. Why? Because link length is a physical variable that cannot be negative. In the sense, the direction of xi should be properly assigned in such a way that the link length never be 0, or you can say never be negative, not never be 0, never be negative. Okay, so in that condition we will actually like go forward. So we would be using the non-standard Dynavit-Artenberg representation, in the sense, you know, like you can see the arm matrix, or what you call general arm matrix or transformation matrix for I frame to I minus 1 frame. This is what the relation. So now we will go to the real system. Okay, the real system, you can see that the same manipulator, I am just showing it. You can clearly see. So the positive axis is actually like coming in this way. So obviously the joint axis Z1 is here, and Z2 is here, and Z3 is here, and Z4 is in this direction, right? And in addition to that, you can see that there is a distance here, 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 and there is a distance here. Okay, and you can see this is a rotary axis, so I can actually like make it, these two are parallel. But if you look at in the top view, it is like this, right? But what we are trying to see, we are trying to make it, this is parallel. So that is what we are trying to do. In that sense, if I actually like draw in a simple way, you can see that this is the first point, which is the base, and you can see that there is a hitting point, the intersection, and there is another hitting, there is another intersection. Then you can see these are the points are coming, right? So now what we need to do, we need to actually like fix the z-axis. So z-axis, you can see like the z-axis direction is this z1, and this is the z2, and this is the z3, this is the z3, and this is the z4 direction, right, based on the positive rotation. Now where we will fix the frame. So now you can see that z1 and z2 are parallel. So you can see there are n, you can say infinite number of common normal you can draw. So I'm actually like seeing that this is actually like the starting point. I fix the one here, and you can see these two can be easily addressed. This can be addressed along x, and this can be along z. So then I can see this point I can take as a 2 frame. And now you can see there is a node here and there is a node here, but the third axis is actually translation axis. So I call this is third, and third and fourth is the tip. So I can call this the fourth. So now you can see this distance I need to cover. I am taking this as 0 frame. Okay. So now what you need to do, you need to actually like fix, you need to fix what? Z0 axis. So I am fixing it parallel to Z1. So now what you need to fix, you need to fix X0. So X0 I can fix it because these two are parallel, and these two also parallel X1, and these two are parallel X2, and this is X3 and 4, right? So when you are fixing Xi, you have to see Zi and Zi plus 1, right? So that is what the rule. So now we will actually like see how that can be go further. You can see this is the line which is actually like connecting all the link length, in the sense frame length, or you can call a line which is like connected this one line, this is second line, third line, fourth line, and fifth line. Okay, this is 1, 2, 3, 4, 5, right? So this is the tool point, and this is the base point, right? So and this is what we are doing, and now we will fix the joint axis. This is Z1 is passing through this line, Z2 is passing through this line, Z3 and Z4 is passing through this line, but opposite direction based on the given configuration, right? So now, as I already mentioned, so this would be my I like 1, and this is 2, and you can see this is 3 and 4, then this is 0, right? So that is what we are doing it. You can see this is Z0, and this is I'm fixing it 0, 1, 2, 3, 4, right? So now what you need to do, you need to fix x-axis. While fixing x0, you have to see Z0 and Z1 are parallel or non-parallel. In this case it is parallel. I am taking the forward direction as x0, right? So similarly, while fixing x1, you are seeing these two are parallel, so I am taking the link length positive, so I am fixing x1 is in this direction. Okay, so similarly x2 I am taking, because z2 and z3 are parallel, I am taking it. So now z3 is here, z4 is here, and x4 supposed to be, x3 supposed to be in this line or even this line, but I am taking x2 and x3 are parallel, so in this sense I am taking here. So this is x3, and this is the final axis I am taking parallel to x0, so in the sense 4. So this is what we have done. Now we have done the frame arrangement. You see, so easy, right? It is so simple also. So we'll see what we have done. We have done this. So now I am calling this is D1, this I am calling A1, this I am calling A2, and this I am calling D2, and this is I am calling D3. What is that? The distance between this and this, sorry. So the distance between this A2, this is actually like A1, and this is what you call D1, right? So now you can see this is D2. So what else actually like you need? So you can see that there is a 180-degree rotation about x-axis, Z3 to Z4, that angle, right? So now we'll come back to the Danavet-Attenberg parameter. So I is the frame, and ai minus alpha I minus 1, ai minus 1, theta I and di we have to find. So I start with 1. So what is alpha here? Alpha I minus 1, in the sense alpha naught. So alpha naught is actually like here parallel, so 0. A naught is actually like there is no distance along x naught, so that is 0. And you can see that this is actually like active joint theta 1. So I am writing theta 1. And you can see this is the distance, which is d1. I am writing d1, right? So now you can see that the first one we have done, right? So the second axis or second frame, what is that? So the second frame here, so you can see that the second frame is actually like you can see alpha 1. So alpha 1 is actually like here again both are parallel, so it is 0, parallel and same direction, so that's why it's 0. Then A1, you can see there is a distance along x1, so that is I call A1. So then you can see that this is an active joint, so there is a theta 2, and x2 and x1 are parallel, so theta 2 is the variable. And you can see that the 1 and 2 frame, there is a horizontal distance and as well vertical distance. This vertical distance is covered along Z2, so that come under D2. So now we have done, right? So now coming to the third axis or third frame, you can see third frame again Z2 and Z3 are parallel with respect to x2 and same direction, so in the sense alpha 2 is 0, and A2 is actually like there because along x2 there is a distance. This distance I am calling A2, and you can see this distance I am calling D3, but this is opposite direction, so this is minus D3. And you can see x3 and x2 are parallel and the same direction, so there is a 0 degree, right? So now you can see that third. So why D3 is negative? Because Z3 positive direction here, but you are coming opposite direction, right? So that's why it is negative, so that's what minus D3. So now coming to the fourth one, so you can see that Z3 and Z4 are parallel but opposite direction. So about x3 you are rotating 180 degree, so that means alpha 3 is pi and A3 is 0, and there is an active rotation about, you can say, Z4, that is theta 4, and there is no distance, right? You can see we got it. So now we will actually like substitute that into Danavet-Attenberg arm matrix. You will get individual matrices, all 4, and you know like T0 to 4 you can obtain T01, T12, T223, 3 to 4. So you multiply in series. So what you obtain, that is what you call the final matrix. So the nth frame with respect to 0th frame you obtain, and you know this is what nothing but your position vector, and this is what you call rotation matrix. And you can cross check once you obtain this, you substitute theta 1 equal to 0, theta 2 equal to 0, and theta 4 equal to 0. So what you will get this one, so this one would be 1 0 0, and this would be 0 minus 1, and you can see that this one would be 0 0 minus 1, right? So now you can actually like see, so this is what you obtain, and you can cross check here. So what you can cross check, you can cross check here. So Z4 and Z0 is actually like opposite direction, so in the sense the last column is 0 0 minus 1, and x0 and x4 are parallel, so then it is 1 0 0, and you can actually like take a right hand rule. So this is what your y0, but here actually like y4 is here, right? So in the sense, so this is what you obtain, right? So in the sense your Danavet-Attenberg is ready, right, in the orientation side. and in the positional side you can see that what is x-axis displacement with respect to x0 or 0 frame to 4th frame, that is a1 plus a2. What is the z-axis displacement? So d1 plus d2 minus d3. And what is the y-axis displacement? That would be 0. That you can cross check here. You substitute theta 1 equal to 0, then a1, this is actually like a2, and this would be 0, and this also 0. In the sense this is a1 plus a2, 0, d1 plus d2 minus d3, right? So now we can actually go forward. So this is what you call forward kinematic model, and you know these two actually, like if you know px, py, pz and psi, you can obtain inverse kinematic model. So in this sense you can actually like do this. So this is actually like simple 2R serial manipulator case, and this is actually like obtained from the forward kinematic model, right? So in the sense you can see that we have not done any complicated, right? You see we have taken a real-time manipulator and we have done it, right? So that is what more important. You see this is very realistic, right? But we have done. So that is what we have to see. And next you can say class I will take a very complicated manipulator and then we will address. So with that I am closing this particular supplement session, and see you then. Bye. Take care.